All right, everyone, welcome to the DDPS seminar. Before we introduce our invited speakers, let's go over some rules and logistics. First of all, please mute yourself during the talk, but if you have questions, you can unmute and ask questions, of course. Or you can use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences, so no classified discussion, okay? And finally, the talk today will be recorded and uploaded in our YouTube channel. All right, that's about it. Let me briefly introduce our speaker today. It is an honor to host Dr. Nicholas Ball, who is a researcher fellow in mathematics at the University of Cambridge. He obtained a PhD in numerical analysis in 2022 at the University of Oxford under the supervision of Patrick Farrell and Alex Townsend. His research focuses on the intersection between numerical analysis and deep learning with a specific emphasis on learning physical models from data, particularly in the context of partial differential equation. He was awarded a Leslie Fox Prize in 2021 for his theoretical work on PDE learning. Today, Nicholas will give an exciting talk on elliptic PDE learning that is provably data efficient. Before I pass the baton to Nicholas, let me ask a couple of questions to Nicholas just to get to know him better and make this seminar somewhat informal. So, Nicholas, I'm going to ask you a couple of questions, if that is okay.
Sure.
All right. The first question goes, you seem to be very passionate about data-driven PDE learning and data-driven approaches in general. Is there any moment in your life when you realized that, wow, this is it. This is the field I would like to commit my career?
Yeah, well, so I started to work on numerical solvers for PDEs, and I saw the recent excitement about AI, machine learning 5 years ago, and particularly the landmark paper by Karnadakis and his co-authors on physics-informed neural networks as well, that were first trying to merge the field of machine learning and PDE. So I found it was very exciting and started to work on these questions as well.
Okay, good. Sounds good. The second question is, would you tell us one good thing about where you are right now, the University of Cambridge?
Well, I think it's a good thing that is like the great amount of researchers in like the related areas that we have. Like we have lots of people working on inverse problems, on classical numerical analysis, fluid dynamics, and so it's always very interesting to see and discuss with like such a wide variety of researchers here in the university.
Awesome. Well, the floor is yours, Nicholas.
Yeah, great. So thanks for the introduction and thanks a lot for the invitation to speak today. So I'm going to talk about PDE learning, and this talk is based on a recent work with my collaborators Diana Alikias and Alex Townsend, who was my former PhD supervisor. And so before I thought I would just give a very brief introduction to the field of scientific machine learning. And so basically, so you're all aware of the vast and recent successes of deep learning and machine learning to various scientific fields like natural language processing, image classification, speech recognition. And so in the past few years, so researchers from numerical analysis started to exploit and work toward exploiting these techniques from deep learning and combine them with numerical analysis and physics. And so the idea behind being that if we collect enough data from physics experiments, then we might want to either simulate numerical solvers or learn mathematical models for experiments. And so there's a great review paper by Karnadakis and his co-authors on these topics in Nature Review Physics and Physics Informed Machine Learning. And so in this talk, we'll be focusing on PDE learning. So I like to think as scientific machine learning as being the combination of three main research areas that are interlacing machine learning and partial differential equations, or PDEs. So the first one is PDE solvers. Then we have PDE discovery and PDE learning. And so all of them are different flavor of scientific machine learning, which are addressing different problems. So typically, PDE solvers is aimed to construct deep learning algorithms to solve a known PDEs using data. PDE discovery is try to find coefficients, to discover coefficients of a PDE, assuming that we have a certain prior on the form of the PDE, using, for instance, the Cindy technique. And finally, PDE learning aims to discover mathematical models from data with very little prior knowledge of the physics that simulates the data. And so for instance, of PDE discovery, so I just want to illustrate an example of potential application. So this is showing a picture extract from a video of surgery that people have done on a pig's brain. And so from this type of data, we would typically like to extract some biological tissue properties without having to perform expensive and difficult in vivo surgery. And so this is typically belongs to the field of inverse problems, where from indirect measurements of a phenomenon, we would like to extract some properties, some tissue properties, or if you are more from the PDE community, some coefficients like diffusion coefficients happening in the PDE. Another field is another example for another field for PDE solvers is that's a paper from K and Hall in 2021, which shows a fluid flow over an espresso cup. And so in this paper, the authors only have access to snapshots of the temperature measurements of the fluid above the espresso cup. And from that, assuming that we know the underlying equation that governs the data, we would like to infer other variables like the fluid velocity and the pressure. And so this is a great example of application of a technique called physics-informed neural network, which aim to train neural networks to fit or to approximate the solution to a given known PDE. And finally, the last field, which is a field where I'm focusing on, is the field of PDE learning or operator learning, where we don't necessarily know what the model is, and we try to infer the model, so approximate the action of the model on some input data. So typically in this example, we have I'm showing you a picture extract from a simulation, a fluid flow simulation, where the fluid is going, a jet flow simulation, the fluid is going from the left at high velocity and traveling to the right. And so if we are interested in applications like material designs or optimizations or fast simulations, we might want to build a reduced order model of the system to, for instance, just map the incoming boundary fluid at the left to the outcoming fluid velocity on the right, without simulating the full model, which might be very expensive. And so we might want to build a reduced order model using PDE learning to speed up numerical solvers. But there are also occasions where we don't know what the underlying physics is. We might just acquire data from physical experiments and try to build a mathematical model using machine learning. And so in this talk, we're going to focus on PDE learning. And so in particular, we want to learn solution operator associated with partial differential equations of the form L of U equals F. L, you can think of L as a linear PDE, where U is the solution and F is a source term that excites the model. So typically what we have is we have observation data. So F is like our input to the system. So it's like a parameter that we can vary, it's the function that we can adjust. We send this function to the system, and then either we perform a numerical simulation or we perform a physics experiment. and we acquire the underlying solution, so the response of the system to our input f, u. And so the response is denoted as u. That's the underlying solution of the p that we assume to be unknown. And so the main contributions that I will describe in this talk is first a theoretical results that quantify how many training data f and u are needed for training those systems. And the second contribution in the second part of the talk will be a practical deep learning approach to learn Green's functions, which are an example of solution operator. And the key ideas behind our results will be based on numerical linear algebra, in particular randomized numerical linear algebra, result concerning regularity of Green's functions, and rational neural networks, which I will describe later. And so there are several standard approaches for PDE learning. So typically, we aim to approximate solution operators that are denoted by L-1, which are operators between functions. And so the classical approach is that we sample random functions f, and then we acquire associated solutions u. And from these pairs f and u, we want to approximate the operator that takes in any function f and returns the corresponding solution u. And so the way researchers are doing that now is that they build a neural network model that approximates this operator. And the neural network model is called a neural operator by analogy of being a neural network in infinite dimensions, so mapping between functions instead of mapping between real values. And so while it's expensive to train these networks, the idea is that once the network is trained, then it's extremely fast to evaluate and often faster than standard numerical solvers. And so the classical approaches for doing that are the DeepNet, the Fourier neural operator, or the deep green. And there are also lots of recent papers on proposing different techniques for building neural operator. And so essentially, all these approaches differ by the type of neural network architecture that is being used. So the DeepNet is based on two fully connected neural networks. The Fourier neural operator is based on convolutions and the fast Fourier transform, while the deep green approach is based on autoencoder. And so depending on the prior physics that you have on the operator, you might want to prefer using one approach or another. But all of these approaches are essentially trying to approximate the solution operator with different prior on the type of architectures that they use. And so there are different challenges right now that we see in PDE learning. So first is the lack of theoretical results. So there are different questions that I want to look at, which are, for instance, what type of training data and how much training data is needed to train these neural operators, getting rigorous performance guarantees with rigorous error bounds, understanding what type of neural network architectures are better than others. So these are typically approximation theory questions, or whether these approaches are robust toward noise perturbation. There are also some practical challenges related to the interpretability of the model. So the approach that I mentioned are essentially black box in the sense that these neural networks objects are very complex. And so it's very difficult to get some interpretations once we have trained a model, because since those are related to physics application, we might be interested in extracting physics knowledge from a model, such as dominant modes governing the system behavior, the symmetries, conservation laws satisfied by the system, or singularities, shocks, location, and etc. And so in this work, we'll focus on trying to understand how much data do we need to learn solution operators. And so I just first want to show you these experiments that I did, where I trained 3 types of neural operators to approximate the solution operator of Poisson equation. So that's a very simple model, just like a toy model in 2 dimensions, just to test the behavior of these models. And so what I'm doing is I generate random source terms, f, to Laplacian u equals f. And then I simulate the solution. I solve the PDE, the associated equation to get the solutions u. I train the different models for different size of the training data sets for different numbers of training data. And I report the testing error that we get, the relative testing error. So typically we see like a sharp decrease in the testing error as the size of the training data set increase towards 50, and then kind of the stagnation of the error towards 5% relative error. And so here, this is a kind of a very interesting observation in the sense that we don't need that much data here. We need like something like 100 or 50 source and forcing them to approximate solution operator well with 5% error or 2% error. And so this contrasts with the vast amount of data that is being used to train traditional applications of deep learning, such as for image classification or natural language processing. So
I have a question, Nicholas.
Yeah, sure.
Here, when you generate the data, the sampling procedure is also a factor of this performance measure.
Yeah.
Like whether you use the uniform sampling, light and hypercube sampling.
I'll talk about that a bit. It depends on what kind of distribution you use to sample the source term for sure.
Okay, got it. Okay.
So a key question is to understand how much training data do we need to learn a PDE. And so there are several works recently that have been studying this kind of behavior as well. And so first here, we'll focus on, to try to understand this question, we'll focus on linear differential equations of the form L of u equals f, where we know that we know the form of the solution operator. So we know that the solution operator is an integral against an object called the Green's function. And so we know that if you know the Green's function here, then you can express the solution operator as the solution to the PDE as u equals integral of g times f. And g is basically represents the solution operator to the PDE. So if we know g, then we know the solution operator. So as an example, if we look at the Poisson equation with homogeneous directly upon condition, then we have this Green's function below. And so it's interesting. So from the Green's function, we can read certain physical properties of the underlying equation, such as the symmetries are related to the symmetry, to the fact that the PDE is self-adjoint, or the boundary conditions can also be read on the Green's function. And this is the same for a slightly more complicated example, which is Helmholtz equation in 1D, where we can read the Helmholtz frequency on the wavelength of the Green's function as well. And so in our case, we'll consider elliptic equations in 3 dimensions of this form, so diffusion type models, where A of x here is a matrix of coefficients. And so we don't know what the coefficient functions is. And from these equations, we would like to learn the corresponding solution operator or the Green's function. So we excite the system with different source term f, we read the solution u, and then from that we would like to derive an algorithm to approximate the Green's function. And so our main theorem states that there exists a randomized algorithm. So our main theorem constructs a randomized algorithm which converges exponentially fast to the Green's function with respect to the number of training data that we use. And so the algorithm is random because we used a random source term sample from a certain Gaussian process that we characterize. And we also because it's randomized, so we get a theoretical bound with a certain probability of success. And we show that the probability that the bound fails is exceptionally small. So it decreases exponentially fast as well as you increase your amount of training data. And so the proof that I will describe later on the slides combines different techniques from numerical analysis and generalize them to infinite dimensions. So it combines randomized singular value decomposition, hierarchical matrices, and peeling. So now we'll go through the proof, so through the different aspects of the proof to construct the algorithm that converges to the green function. So first we'll go through randomized numerical linear algebra. So if we have so we'll come back to finite dimensions first, and then explore how we can extend these results to infinite dimensions and learning Green's functions. So first, if we have a matrix A, then we know that we can write down its singular value decomposition, and that the Eckart-Young theorem tells us that the best Ranke approximation to A is given by the truncation to the case singular value, and the error is given by this epsilon k here, it's given by the tail of the singular values. And so a landmark paper by Halko, Martinson, and Chop in 2011 called the randomized SVD tells us that if we have a black box matrix A that we can only access through matrix vector product, then we can construct a low rank approximation to A from random input vectors. And in the paper, the authors describe this algorithm and also prove rigorous convergence, rigorous results to guarantee that the algorithm converges. And in particular, it shows that the probability that the approximation is close to A is very large, and the bound depends on the best Ranke approximation error epsilon k. And if you compare against the best Ranke approximation, basically the randomized SVD algorithm performs only slightly worse than the best Ranke approximation error. So in blue, it's a randomized SVD to approximate a low rank matrix, and in black is the best approximation as I increase the number of sample vectors. And so traditionally in the randomized SVD, the random input vectors are sampled from a Gaussian distribution. And here we're interested in extending these results to correlated Gaussian vectors so that we can later extend them to infinite dimensions. And so that's what we did in a paper with Alex Thompson a year ago, where we essentially extend the bounds from the paper by Halko, Martinson, and Chop, so that we allow the randomized SVD to work when we have a correlation between the entries of the input vectors. So we have essentially the same type of theorems, except that we have a factor here, beta k over gamma k, that depends on how correlated the input vectors are. And a nice feature about this construction is that this additional factor here, the fact that we allow this additional flexibility, so the fact that we allow for correlation between the input vectors in the randomized SVD, allow us to enforce prior knowledge of the matrix A that we want to approximate into the design of the covariance matrix from which we sample the random input vectors. And so if we have some prior knowledge on A, we can basically enforce that into a construction for the random vectors. And in some occasions, we can get better approximation error than the randomized SVD. That's what the plot shows on the right, where we normalized the error by the best approximation error. And in some cases, using a carefully constructed random vectors, we can get 40 to 50% better performance compared to the randomized SVD. And so now that we have this generalization, we can basically extend it to infinite dimensions and to operators. And so we'll consider Hilbert-Schmidt operators, which are bounded operators between binary spaces with finite norm. And so essentially what the idea is that the Hilbert-Schmidt operator are the natural generalization of matrices to infinite dimensions, in the sense that they enjoy the same properties. So the Hilbert-Schmidt norm for an operator is equivalent to the Frobenius norm of matrices. So it's the square root of the trace of A star A. So they can be seen as integral operators if you want. So instead of having matrix vector product, we can have integral of g of xy times f of y, and the two behave in a similar way. And so they have nice properties. So if you have like an Hilbert-Schmidt integral operator, then the Hilbert-Schmidt norm is the norm of the kernel G. The L2 norm is equal to the kernel norm of the kernel G. We also have a singular value decomposition for Hilbert-Schmidt operator. And we also have an Eckart-Jung-Mirsky theorem, which tells us that if we truncate the SVD, we also obtain the best Rankine approximation in the Hilbert-Schmidt norm, which is the analog of the Frobenius norm. And so essentially what we have here is that we have all the ingredients for extending the result that we have for the randomized SVD from matrices to infinite dimensions with Hilbert-Schmidt operators. So now instead of approximating, computing a low rank approximation to a black box matrix A from matrix vector products with random input vectors, we can compute a low rank approximation to a kernel G from integral against random functions f sampled from a Gaussian process. And the idea is that because we have this nice theoretical setup, all the algorithm and the theory extends really very naturally to infinite dimensions. And so now we have, instead of having covariance matrix, we have a covariance kernel from which we can sample random functions from the associated Gaussian process. And the choice of the covariance kernel will influence the distribution of the random functions and the approximation error rate that we observe at the end. And so that's our theorem then. So if we have a kernel G, then we can construct an approximation using a certain number of random input functions sampled from a Gaussian process that basically satisfy this error bound, where epsilon k here, which is the main error factor, depends on the best Rankine approximation to G. So it depends on how fast the singular values of G decay. And this gamma k factor here is basically determined by the choice of the covariance kernel. So how appropriate is the covariance kernel for learning the dominant singular vectors of the kernel G. And so this is showing an application of the randomized SVD for Hilbert-Schmidt operators. So on the top left, we have the exact kernel that we want to approximate. And on the bottom right, this one is a learned kernel from the randomized SVD. And so in this example, I'm using random functions sampled from the squared exponential kernel with different length scale parameter. So in red, I'm using a very small length scale parameter. And in blue and green, I'm increasing the length scale parameter. And as I vary the length scale parameter, we see that we obtain different relative error, and that a small length scale parameter here is better for learning this kernel, because essentially the eigenvalues of the covariance kernel will decay more slowly. And so we are able to generate a larger finite dimensional vector space of random functions for approximating the kernel. But if we choose the length scale parameter correctly, we can approximate this complicated kernel to nearly machine precision with the randomized SVD. And so now that we have this generalization of the randomized SVD, we can apply it to learn Green's function and to construct an algorithm for learning Green's functions. So we have this Green's function here. We use the randomized SVD. We compute integral against the random functions that we sample. And then we apply the error bound that we derive, where we have to characterize what this epsilon k factor here. In other sense, we have to understand how fast the singular values of the Green's function decay. The problem that we observe here is that the Green's functions are not smooth near the diagonal. So in 1D, there is a discontinuity in the derivative. And in higher dimensions, so in 3 dimensions, Green's functions take even infinite values along the diagonal, which is problematic in this case. So this basically, the fact that the Green's functions are not analytic and they are not smooth, tells us that this epsilon k decays very slowly with k. So in particular, epsilon k decays algebraically with k, while we want to reach an exponential convergence rate to match what we observed in the deep learning experiment that I showed earlier. So how do we solve this? So we are going to exploit regularity results about the Green's function. And so in particular, we go back to a paper by Bebenoff and Hackbush 20 years ago that showed that even though Green's functions are not smooth, and so they are not low rank on the entire domain, they admit a low rank structure on well-separated subdomains. So if I'm taking Green's function here on the cube in 3D, if I restrict it to two subdomains that are well separated, such as the green and blue domain, then we know that on the cross product of this subdomain, the Green function is smooth, globally smooth, and will be low rank. But if I take two domains that are attached to each other, such as the blue and red domains, so these two domains are touching each other, here the Green function is not smooth. So these are domains that are lie along the diagonal of the tensor product omega cos omega. And so if we look at a one-dimensional picture here, so this is the Green's function for 1D equation. So the Green's function is a two-dimensional object. This is, in this case, I'm coloring domains that are well separated. So I'm doing what's called the hierarchical refinement. So if I take two domains that are well separated, I color them in green. And if they're not well separated, I can do a subdivision of these domains and look at whether the children are well separated or not. So if we start from away from the diagonal, and then we progressively refine the domain as they go smaller and smaller towards the diagonal to capture the different low rank domains of the Green function. And so now that we have this hierarchical construction, the idea is that we can look at each green domains where the Green function is low rank. So because it is low rank, it's well approximated by a low rank function. And this tells us that this the singular values, the tail of the singular values, so this epsilon k here, is smaller than epsilon and decays extremely fast with respect to k. So this the singular values decay exponentially fast with respect to the rank k here. And so in particular, this tells us that we can apply the randomized singular value decomposition on each subdomain and get a very good approximation to the Green function with a low number of training data. And so what we do now is that we do it in a hierarchical way, in the sense that we first learn the larger domains first, and then we progressively refine, go down the hierarchy, and refine the results towards the diagonal. And so we have we use a clever algorithm called the peeling algorithm that have been proposed by Singing and collaborators and Martinson as well about 10 years ago, that allows us to reuse as much training data for the randomized SVD as possible to exploit the hierarchical structure of the domain and limit the number of data that we are using in our algorithm. And so now that we have that, we just have to deal with the case of the diagonal. So we just have to deal with the red subdomains here, now that we have approximated the Green function on each green domain with the randomized SVD. And so what we are doing now is that we look at characteristics of the Green function. So how the Green function decay away from the diagonal to characterize the magnitude of the Green function on these red domains here. And here we exploit another result from Elliptic PDE theory from Grutter and Widman in 1982, which tells us that the Green function are smooth and they decay of the diagonal with a certain rate, 1 over x minus y. And so if we integrate over this area of the subdomains, then we can basically essentially construct a hierarchical structure, refine along the diagonal until the Green function becomes, in magnitude, becomes smaller than epsilon. And in this case, we truncate and approximate the Green function by 0 and make error epsilon. And so this procedure ensures that we basically make error epsilon on each subdomain. So when we reconstruct the Green function, we make a global error epsilon. And so in summary, we show that our algorithm achieves exponential convergence rate with respect to the amount of training data. So it doesn't require a lot of training data, which match the experimental behavior that we observed before. And so this tells us that if we consider the class of elliptic partial differential equations in the form that I showed earlier, so in divergence form, this class is data efficient in the sense that we can construct a rigorous algorithm that achieves exponential convergence for learning any Green's function associated with this class from input and output data. And so our construction exploits the randomized SVD and generalize it to infinite dimensions, and as well as properties, elliptic regularity properties of the Green's function, such as its hierarchical lowering structure. And something interesting to mention is that some of the techniques that I described earlier, so the randomized SVD and the hierarchical approximation, naturally extend to other type of equations, such as time-dependent PDEs of this form. So you can think of it as heat-like equations. And so we have a recent paper that describes how we can extend these techniques to time-dependent PDEs as well. And so now in the second part of this talk, I want to talk a bit about deep learning applications. So where we use this type of Green's function learning to design a practical deep learning algorithm for learning the Green's function in practice. And so what we do is that we first start with the point A here, where we select a covariance kernel, so typically a squared exponential kernel. We sample random functions that we use to excite our system in B and C and observe or measure the corresponding solution. So we typically do it by numerical simulations, but you could also do it on practical data that you acquire. And then we formulate our loss function that basically has an object that is going to learn the Green's function. So in the loss function, the ng here object is a neural network that aims to approximate the underlying Green's function. And so we consider with this method simpler PDEs than the ones considered by DDPS or FNO, but where we want to learn a physical object. So we consider simpler PDE, but we want to extract more physical understanding from the model. And so in this case, we have a network for learning both the homogenized solution, which captures the boundary conditions, and the Green's function as well, which is essentially the solution operator. And the idea is that once we have learned the Green's function, then you can extract a lot of features about the underlying PDE. So you can look at potential symmetries of the Green's function, which are related to symmetries of the underlying PDE or conservation laws of the PDE. We can perform a signal value decomposition to extract the dominant eigenvalues and dominant modes. These are related to the ones of the underlying PDE as well. Or look at singularity location. And so this last point here is related to the type of neural networks that we use to learn Green's function. So as I said earlier, Green's function can be singular and are in general singular along the diagonal of the domain. And so in particular, we can't really use traditional neural networks to approximate Green's function because these neural networks, based on, for instance, on the value functions, are bounded. And so we found that using a different type of neural network called rational neural networks, which are neural networks with rational adaptive activation functions, yield better approximation result when trained in this setting. And so these neural networks can have poles. So in particular, they can take infinite arbitrary large values, which is ideal for learning Green's function, which are unbounded objects. And also they support feature instruction in the sense that you can visualize the poles of the underlying rational functions and of the underlying rational neural networks to estimate whether there is a shock or a singularity happening in the model. And I'll show you an example in the next slide. So as an example, if we consider the 1D advection diffusion equation, where I'm turning on advection only on the right part of the domain. So I'm considering this equation on the interval -1, 1. I'm turning on the advection part with this blue term here only on the right half of the domain. I'm training my neural network to approximate the underlying Green's function from pairs of source term F and solutions U. And so what I observe is obtain this Green's function object here. And so first, there are interesting things to consider here. So if we look at the Green's function and we restrict it to the bottom half of the domain, the bottom left part of the domain, then we recognize a behavior, a Green function that is characteristic of diffusion of the diffusion equation. So we can tell that there's a diffusion phenomenon happening on this part of the domain. On the other hand, if we look at the upper right part of the domain, we can tell that this is advection dominated, as the Green function is has larger values in the upper half of the domain. If we now look at the homogeneous solution, so first you can see that there's a really good correlation between the exact homogeneous solution and the one that we learn by our neural network. And now if we plot the rational functions that approximate the homogeneous solution on the complex plane, so even though it's a real function, we can evaluate the rational neural networks on the complex plane, and we get this phase portrait on the right. And this phase portrait tells us that the pose of the rational functions tend to cluster towards 0. So these like dots, these colored dots that we see, these represent the pose of the underlying rational functions. They tend to cluster towards 0, where there's a discontinuity happening in the homogeneous solution. And so this can, by looking at how far the poles are clustering, we can identify some physical properties of the underlying function. And so as a last example, I just want to consider the Stokes flow example in a lead-driven cavity. So it's a two-dimensional vector example, where on the top left first, I'm showing the exact homogenized solution velocity field. So this is the magnitude of the velocity. And the bottom left is the learned homogeneous solution by the neural network. So we see that we have a very good agreement, even though we are using a coarse grid for training our network, between the learned and exact velocity field. And then on the right, I'm plotting the Green function associated with this system, with the Stokes flow. So what I'm taking as input here is the X and Y component of the source term, of the body force term. And I'm trying to learn the operator that takes in the left and right component fx and fy, and output the left and the first x and y component of the underlying solution velocity field. And so in this case, because we have a system that takes in two functions and output two functions, we have what's called a matrix of Green functions, which basically takes these two components and after convolutions output the two components of the velocity field. So these are the G11, G12, G21, and G22. And the interesting part is that by looking at the system, at the Green function and the symmetries, we can understand first symmetries of the system and how the X and Y component of the velocity are correlated with the X and Y component of the source term, and how the system correlates and correlate those components. And so to conclude, in this talk, I described a theory for learning Green functions. So we showed that we can achieve exponential convergence rate when learning Green function, which is in agreement with state-of-the-art numerical simulations, deep learning simulations that have been performed in the past few years. Then we constructed a generalization of the randomized singular value decomposition to infinite dimensions and Hilbert-Schmidt operators. And also I described the deep learning approach. We have a package available in TensorFlow for learning Green function that use rational neural networks. And so with that, I'll conclude, and thank you for your attention, and I'm happy to take any question.
Thank you so much for the wonderful talk, Nicholas. Let's have a Q&A session. Awesome. I don't see any questions in chat room for now, but that doesn't mean you cannot ask questions. Let me start with my questions. So is it only applicable to linear elliptic problem for now, or can it be?
Yeah, so this main theory that I described is for linear elliptic problems, because we need some underlying results on regularity theory that is done for elliptic problems, and can also be extended to parabolic systems. So the equations are similar to the heat equation. a key question, of course, a key challenge for the future is to extend these techniques to hyperbolic PDE, which would be very challenging, and also nonlinear problems. So that's a key open questions for the future, is to get some theoretical results to quantify sample complexity of PDEs for hyperbolic systems and nonlinear PDEs as well.
Okay. And also, I have an impression that this only works for the uniform mesh.
No. So actually,
or the Cartesian.
no. So in the loss function here, I have this integral operation. So we have this green function that takes x and y as input. You can discretize. You can take any quadrature rule as you want. So you can discretize your mesh, your domain as you want. Take any quadrature rule, and that would work. So if you don't have any strong a priori on the domain, you can use like a Monte Carlo approximation and take random points in the domain. But you can also use more like higher order and more fancy quadrature rules if you have access to.
Okay. Awesome. Can you tell us about what kind of like speed up you obtain?
So
yeah, go ahead.
So the theoretical results that we have is not meant to be applicable in practice. So because constructing the hierarchical structure could be quite challenging if you have complex domains. So it's mostly there. So we mostly try to understand what type of distributions of source terms are interesting in applications and try to give rigorous guarantees for existing state-of-the-art deep learning techniques. As for the speed up, so it's still an ongoing works right now to really evaluate those techniques against classical solvers. So I'm not really advocating that we should use these techniques to speed up numerical solvers, but I'm more confident in their utility where we don't have a model for them. So I prefer to use neural operator techniques for cases when we don't have any model. Like for instance, there are recent applications in the team by DeepMind and in Caltech as well to weather forecasting, where we don't necessarily have a good model for weather forecasting, and in this case they achieve some huge speed up compared to existing techniques.
Awesome. Okay, so for example, weather forecasting, if you want to use this method, probably the data we collect is huge.
Yeah.
So if you can talk about the scalability of this method as the data size increases, the cost of learning those Green's functions, does it scale linearly or?
Yeah. So I believe here it's yeah. I believe this would scale linearly. Yeah. I mean the training of the neural network. Yeah, I believe this would scale linearly. And the whole point is that because we have like such, in this case, prior information, you don't need much training data as well, because the idea is that because the PDE and the solution operator has a lot of structure, in practice, you don't need much training data to train them. So the experiment I showed here in 2D with Stochflow, we are only using like 100 source and solution terms.
Well, I don't think the neural net training cost is scale linearly with the data size. You have to solve a nonlinear optimization problem.
Well, because if you do like batch, use like batches, like batch optimization, I think at each epoch, the number of iterations that you do over your batch set is increased linearly with respect to the underlying dataset size. So all the updates that you are doing, like stochastic gradient descent updates, is fixed and doesn't depend on the dataset size. and then each batch, in this case, this will scale linearly with respect to the size of the training data.
Yeah, the problem is, when you increase the data size, the parameter you have to introduce weights and biases in the neural network, it increases as
for
well.
sure. Yeah.
So the number of unknowns in your nonlinear optimization problem is increasing, and search,
sure. But I'm not saying that this method should compete are trying to replace standard classical numerical solvers that have been heavily optimized. I think these methods are interesting in the case where we don't have any alternative. We don't know what the model is.
I understand.
We need to discover we want to discover some physics. That's really my point on this class of
yes, I mean, in that sense, this method is very promising. Okay. Any questions from audience? I mean, unmute yourself and ask your question.
Oh, I asked a question in the chat.
Oh, you did?
Yeah.
I did not. I don't see any. Oh, sorry about that. I missed that. Well, question from Rui. He asked, can you comment on the relation of your method to FNO?
Okay, so that's a great question. So the FNO, in a sense, is also trying to learn like a kernel, like a Green's function if you want, but it's doing several layers. So it's like if you want, our method can be seen maybe as like a one layer FNO, where we don't do extra. So in the FNO do extra approximation, extra simplification of the type of kernel that they use using the Fourier convolution. So our method is more simpler than FNO. It only works it's much more limited because it only works for linear PDEs. But then we allow for learning a much more diverse class of kernels. So because we construct an object to learn the Green's function here, the advantage is that we can really visualize the object that we get, whereas FNO is kind of more like a black box neural network architecture, so it's much more difficult to extract some understanding. So our approach is more like a one layer, can be seen maybe as a one layer Fourier neural operator, where you replace the convolutions by this neural network G here.
Also, related to that, how about compared to the Cindy?
So that's another great question. So the Cindy approach is basically, so if you remember at the beginning of the talk, where I show this figure here.
Mm-hmm.
So FNO, DeepNet, and our approach are in PDE learning, on the PDE learning side. PINS is in the PDE solver, so physics is for neural network, and the Cindy approach is more on PDE discovery.
Mm-hmm.
So they have some knowledge of the type of equations that they want to recover, and they try to learn coefficients of the equation. So the Cindy approach, in a sense, is complementary to the PDE learning approach. So they have stronger prior on the type of physics that they learn, but they try to recover different information. So these two are complementary approaches.
Okay. I mean, I would view it like Cindy as a ODE learning or the PDE learning as well. It does give you some differential equation form.
Yeah, exactly. So I call it PDE discovery in the sense that you are trying to solve the inverse problems. While PDE learning, you learn the forward problems with the solution operator.
But the form is not PDE, right?
No, it's not a PDE. But if you use the Cindy approach and you learn the PDE, you still have to solve it afterwards.
Sure.
Whereas
But both of them are, once those training is done, like the discovery is done, you can use those model to replace or you can use that as a model to find out the new solutions and.
Yeah, you still need to solve the equation.
Exactly. But the PDE learning. Okay, so your point is for the PDE learning.
Yeah, so
you only need
those
to
are
evaluate.
Exactly. So those are really complementary. They will give you different type of information about the PDE. The CDE approach gives you more physics information because it really gives you the coefficients of the PDE, while the operator learning or PDE learning approach, like FNO, gives you more like a fast solver, which may be very useful for optimization tasks downstream, for instance.
Got you. Well, thank you, Nicholas. Is there any other question?
I have a question regarding the linearity of these PDE problems. Hey, Nicholas, I'm Tony. So just to make sure I understand what you mean by linear problem, suppose you have two forcings, A and B, and then you have a new forcing that's a linear combination of A and B. Do you expect the response to be the same linear combination of the response that came from A and B respectively?
Yeah.
Okay, then in that case, if you collected enough forcing and response pairs, and your goal is to solve for a new forcing, can you somehow just find the best linear combination from the data? Like you use a linear combination of the forcing from the data to approximate the new case. And the same linear combination of the response would just give you the best estimation of the response. Am I thinking about that problem correctly?
Yeah, possibly. But I guess if you do that, I'm guessing that that's possibly equivalent to finding a low rank approximation to your problem. And so that will converge quite slow. So there might be better ways than just trying to find a low rank, like a small number of functions in your data set that describe your data. There might be better ways of to compute the solution than just compute an approximation on this small subset.
I see. And is learning the Green's function a way to impose constraints?
Yeah. So yeah, exactly. So if you so what we do here is that in our algorithm we enforce the hierarchical structure of this of the Green's function, and so there are different approaches. So all the operator learning approaches that have been proposed recently, like the FNO, the DDPS, in a way they are all related to Green's function, and they all enforce different type of structure on the model. So if you know the type of structure of the Green's function, like it is low rank, it has a hierarchical structure, it decays away from the diagonal, you can select your neural network architectures to enforce this constraint strongly when you train your network.
Okay, thank you.
Thank you, Nicholas. Is there any other question? Well, if not, let's thank our speaker, Nicholas, for the wonderful talk and nice discussion in Q&A sessions. And yeah, thank you so much, Nicholas.
Yeah, thanks
That's
a lot.
wonderful. Let me stop the recording.